involved here. Another one motivation we are pushing to experiment to confirm that one. So basically, there's a because of that limit by the kinetic energy, recoil kinetic energy, nuclear kinetic energy. If it's 1 GeV, you will have 1 millionth. That's 1 electron or 1 keV. But if it's below 1 GeV, you will have a really small nuclear recoil energy. That is very difficult to measure. There is one main motivation. We are going to search diameter electron. Electron is much lighter, and you have more kinetic energy recoil. So that is motivation. For the motivated by many people more than 10 years ago. So consider light diameter more than 10. For example, this is vector photon diameter effect with the Stern model through the dark photon. For example, this is one example exemplified in this theoretical papers. So we will have some mixing, kinetic mixing angle with photon and dark photon. Then the diameter electron recoil scattering cross-section can be written here like this. Then the event rate, for example, the previous nuclear interaction, we have exponential decay the nuclear recoil event rate, but here also diameter electron recoil event rate can be is proportional to the diameter electron cross-section and also form factor here. So that's the main conclusion from this one. The form factor depends on the mediator. Whether it is larger than electron or we have some scale, much smaller and heavier mediator. Depending on this one, because all electrons are at bound electrons. So that means you will have a form factor depending on the diameter mediator. So this is two event rate proportional to this cross-section, which is physics of diameter and also diameter form factor depending on the detectors. Also, from this experimental theoretical argument, there's also anticipated Migdal effect. This is a confirming experimental Migdal effect is very important, but Migdal effect is correlated with the previous diameter electron scattering too. So there's the common form factor is used. That's theoretically described. For example, here the Migdal effect is if nuclear recoil, not electron recoil, diameter nuclear interaction gives also electron signal. That's the Migdal effect. For example, the Migdal effect final state is excited state because at the low energy, all the atom is involved. Electrons, bound electrons, always involved even with the nuclear recoils. We will have excited state or the free state is also one of the final states. Not only these two, this one, the nuclear recoil, but sometimes very rare, but sometimes we have electric signal is also induced by the nuclear recoil. That is the effect, and they have calculated and this transition probability from the bound electron N shell and L shell, bound electron going to free electrons or excited state electrons are formulated. And but they have the same form factor is used because they also have diameter electron scattering also has the same effect. Basically, we will have same form factor is used in Migdal effect and also diameter electron scattering. There was a main result from this argument. And now I will go to the spin dependent. We have a low diameter, very pursuit, and also at the same time spin dependent interaction is also very less studied. So one experiment towards the effort is going to the spin dependent. Neutron spin dependent was basically liquid xenon experiment also used many other isotopes which included basically naturally neutron spin, but the silicon, although the spin is always there, but proton spin is always occur in special elements in the detector, lithium, fluorine, aluminum, here, sodium and iodine. Those are basically proton R. So we have proton spin, and the recent proton spin experiments one of the most the sensitive experiments was done with the Crest 3 experiment. Has a very low energy, ripple energy. Is observed. Nuclear ripple can be identified, and also they have they can use electron ripple experiment too to get the unanimous through the nuclear effect too. So this is the two experiment that is going to lower energy with the spin dependent, and also lower energy with the electron, single electron, double electron experiment with the diameter electron, and also including that very small energy events, which may be occurred with through the actually we are almost certain to occur with the vehicle. That is the main towards the effort towards the robust diameter. So this is the previous Crest 3 experiment. They gave most of the limit to up to about 0.2 GeV, 20 MeV nuclear recoil. This proton spin and neutron spin has been observed. And so for the total, so this is current small mass, the compilation for all the electron, diameter electron with lighter mediator, the diameter electron with the heavier the mediator, and the diameter nuclear interaction. But you will see very much characteristics here. I want to say this is interesting because they have some argument from the Prof. This scalar solar reflected here bound is given here. So it's not really a direct limit, but kind of if you have a diameter electron interaction, you will have diameter solar electron interaction that reflected to Earth, then inevitable low energy events should be enhanced. So that was calculated, and their limit is given here. So that means this reason is indirectly rejected, removed, but they have to be confirmed very much. But it's a very serious, I think, the limit. But still lower coupling limit. Coupling is very much open. And another one is here. The still most of the stringent limit at very low energy, low mass. This is from diameter neutron is from little xenon experiment, and also single electron measurement with the sensei, the silicon detector, gives most stringent limit. But if you include the Migdal effect, xenon experiment can give much smaller limit, which is dominating now the xenon 2 and the xenon n tone, 1 tone. This limit is here, but direct sensei is also experiment. They have a single electron sensitivity, small size. They have very limit, but they can go a little bit further. But we don't know actually sensei can catch up the xenon experiment. Small. So the nuclear limits are really not from really nuclear recoil measurement. It's really given by the Migdal effect. That's most stringent limit from even for the nuclear diameter nuclear cross section. So this will be improved for general antenna and with NC, LC for these ones. But still, it's really this parameter is still not explored. It's very difficult to go down further. It's a very large parameter space, 10 MeV, and this 35, 36 is difficult to reach. And this, I think, if you go further to the KV diameter, I think this will be the subject from next speaker. So I will not really talk. There's a lot of parameters for the Gomez diameter. So I want to our efforts to clear up the Gomez region, but it's not really much Gomez, but for the Gamma experiment, gave more than 20 years of modulation here as a clear signal of the wave signal. It's actually formulated with some way to it's expected from the modulation from the this Earth rotation from the sun. They gave a modulation, supposed to be give modulation signal if it's mixed with the enhancement at June. So that their data is really consistent with the signal. So there was a challenge by the cosine experiment right here. We have same solid crystal developed by in the United States, but this time we imported the crystal from the United States. So we had a little bit crystal is grown at high altitude, so we have a cosmogenic background is large. So that means we have a decaying component is comparably larger than gamma. Background is also a little bit larger, but gamma signal is more than 10 sigma, and it can be proved, checked with a really higher background experiment too. We are developing further better detectable cosine 100 experiment using the previous drone in the United States. So this is the result of the 3 years of annual modulations from the cosine 100 data, and gives not really to try to give the modulation definite answer, but there's a comparing experiment with Anas and Spain, which has used the same crystals from the same company as cosine 100, and this is the result from the cosine 100 and gamma comparison with the low sensitivity previous modulation signal from the gamma. Cosine has a little bit lower sensitivity for the ability for modulation. But for the standard Hale model, cosine could reject the gamma signal from the standard model, assuming that the model, but not from the direct modulation. But Anas, using same crystals, they have rejected almost with the 3 sigma. They have a larger crystal mass than the cosine 100 with the same detectors. But, so with the 3 years of data, now it's almost, they say, it's incompatible with the lower energy region, more than close to the 4 sigma with the incompatibility with the gamma. So that's one we have observed. And so one thing we have noticed is because of the continuous decaying evacuating the cosine, there may be say something about the gamma liberals method. They have actually always starting from, they have 1 year period, divided the 1 year period, and modulation is observed with assuming they are one constant. So this is the cosine data, but applying the gamma method every year is segmented, and they get a modulation. And another year of data has a modulation, not from the continuous fitting. Like this is cosine way to analyze the modulation. This is the gamma way analyzing modulation. So if we have continuous decreasing, then we will have artificially generated. So this is the apply this method and get this is cosine data. And cosine data shows similar modulation amplitude, but apparently it's opposite sign of the phase. It's not really with the same starting time and ending time was given from the cosine gamma experiment. So they analyzed almost the same way for the last 3 years with the cosine data, and but opposite. So of course this is in the preprint, and they have provocative titles like annual modulation from circular variations of relaxing gamma. That means there was first suggested by theoreticians whether this makes some effect or not. But the another provocative the annual modulation from circular variation, not relaxing gamma. Also because they have a little bit different shape of the, of course the gamma curve also line in preprint playing repeating fit with the linear value. Of course, like same way as cosine, they have not changed their previous analysis. There was officially gamma, so, but they didn't really. What we wanted to have this individual years background level. There was never given by the gamma group, and nobody really knows how they are varied. But anyway, from the official lesson letters like that. So with the, I explained the Migdal effect before. So for cosine 100 explained also Migdal effect was applied to the data. So if we don't include the Migdal effect, this is the nuclear report energy. But if you include the Migdal effect, not very frequently, very rare, but you have a higher energy. This is the energy threshold is one of the most important factors in the raw mass diameter direct search. So this enhancement is really important. And if you include this one from the Migdal effect in the data, and the cosine 100 Migdal effect can give a much stringent reading up to 200 mega electron volt per meter mass. It was not possible this region if we don't include the Migdal effect. And this is the compared with the zero amount. There was the most serious the Migdal effect region for the raw mass diameter as I showed before, and this is the line here. And the other one is especially for the other mass like this Migdal effect from the scintillator, this is quenching factor. Most of that has an advantage from the Migdal effect. But even though the measuring 100% of energy with a cryogenic detector, but still they can have enhancement from Migdal effect, because Migdal effect is actually opening another channel in record energy. So that have also enhanced. And this is a spin dependent Migdal effect, which is which cosine 100 is a little bit better catching up than the spin independent projections. That's expected. For the cosine experiment, we are improving the cosine 100 experiment, cosine 200 with a new detector, new crystals grown in Korea with the altitude, very low altitude, and also the very low point to crystal cool down and to improve the backgrounds. And this is also light enhancement. So this is now anticipating with the cosine 100, improving cosine 200. Cosine 200 will be performed in the Yeongduk lab. You underrun the lab. So this is expected from at the low temperature and also Migdal effect, and including Migdal effect with a higher light output. We can catch up spin independent with close to Gen 1 term Migdal effect to cosine 200. And speed dependent cases will affect with low competition. Maybe there's even the Gen 1 term will affect here, but cosine 200 with proton with including Migdal effect will go down to 20 MeV less region with this about cross sections. So this is what we expect from in the future. And we may enhance this mass further. So another going to, as I showed, another effect or another effort going to the raw mass with a spin dependent, proton spin dependent can be studied at the Univ. With this performance is now measured at the ground level, but this detector will be soon installed in the Univ. But we need to improve a little bit further. Compared to class 3, this is similar to class 3 detector with a different sensor. We are different sensor compared to the other sensors in the return. And this is very promising. We don't have a light detector. We have a PSD without the light detector. We can separate nuclear report. Right now, preliminary energy threshold is a little bit high than another class-like, otherwise-like experiment, but we are catching up the threshold. So this is one of the experimental efforts. I want to have minutes. So I have one more subject as Prof. Hagimara showed the neutrino experiment, neutrino talks. We have a possibility for the Majorana, which is compared to 4 states in the standard model. We may have only 2 states in the neutrino, and the neutrino is this one, and that they actually certainly violate that number of conservation, and also the Majorana mass term can be if it's written like this, and this is the charge convolution neutrino is the same. And that means the Majorana particles and no reference number is maybe needed. this seesaw mechanism conforms this myonuclear nature and gives the tunnel myonuclear mass size very large and very small. So this may be one of the most promising beyond the standard model physics. And how to measure was configured very conjecture very long time ago, 80 years ago, with Fury. At that time, the Fury suggested to measure neutrino risk stability decay to actually measure the stability decay itself. The conjecture was neutrino stability decay may occur much frequently than 2 neutrino stability. That was his original motivation. But eventually, anyway, this original myonuclear conjecture is never confirmed. And that's one of the most important beyond standard model, as I said. So this is actually occurred with at least matching at these 2 points with a small neutrino mass, and the neutrino mass scale will be proportional to this probability of this general stability, which occurred at the 0 vector function with the qubit. This is theoretically driven from the 3 neutrino oscillation parameters, neutrino mass difference, and also mixing and all are included to theoretically derive the stability mass, which is here. They can be calculated very easily with assuming lowest neutrino mass. And so we have 2 possibilities as we discussed previously: inverse mass ordering and normal ordering gives different numbers. We have many parameters here. And so currently, this is the neutrino mass current limit from the zero neutrino beta decay experiment, also single beta decay experiment. Single beta decay has less parameter, and current limit is 0.8 electron volt from cutting. That's not severe, but I think the mass cutting limit is more direct in terms of it has a less parameter, so mass difference, and but the low uncertainty actually. So this is limit from the zero to WK and cosmology cover neutrino mass is more stringent, but this area you need myonuclear neutrinos. So that cosmology has a kind of model dependence. I think the neutrino mass is considered by WK cosmology with a model dependency. But so it's a cutting experiment really important to go down. They have, I think the original purpose is 0.2 electron volt, but now they are going down below 0.8. I think that order limit is one of the most important measurements. Current zero to WK is for these isotopes. Important thing is the 2 neutrino WK, the lifetime. This is one of the most important things to consider by experimentalists. Molybdenum 100 is the smallest lifetime among all of them, and xenon and germanium is one of the largest. So it's a very constrained experimental way, and the best experiment is from Chungnam and Zen. So I will go a little bit on some experiment. Chungnam and Zen experiment loading xenon 136. 800 kilogram in the small balloon, and they have an outer balloon. QP demo is similar to our experiment, more than 100 with the cryogenic detectors. They have about 20 crystals. They have around, they finished so preliminary run. And there's the 200 is going on now with the 200 kilogram of germanium 76 isotopes. So this is the just finished one QP demo experiment. They have a zero background, no events in the ROI reason. This is one of the first zero background events performed with this 1.8 times 24 years limit. And they are proposing, this number may not be very accurate, 270 kilogram of molybdenum 100 with a cryogenic detector soon. This is just reported Chungnam this year in the PRL. This is already published, and this is their 90% confidence level of signal with this background data. So one of the dominant backgrounds from Chungnam Xenon 136 target is the Xenon separation product, which is the one dominant over the 90% confidence signal. And xenon separation background is dominant. Xenon separation means xenon 136 nuclear itself spellate and make a long lifetime isotopes inside the target. So it may indicate xenon the delirium experience may be depth limited. Now there are many proposals. This is one of the plot I showed many times. This is the expected year of the result. This is the neutrino mass. Solid line is already reported the number. This is the expected from the current final goal is around here. Tellurium 4 experiment less than 200, and among 2 we are proposing the expected lifetime at the neutrino mass is around 2029, about this number. This is the current small mass, the total, the expected neutrino mass and beta. This is the invert mass hierarchy minimum, about 18 millielectron volts. So if you go this band is uncertainty from the nuclear metric from theory. And this is a little bit exaggerated among 2 expectations, but more or less this very large experiment with the very large X-axis exposure from the very large size of scintillator with the tellurium genome. As I said, the tellurium genome may be that's limited. This is my bit, but this is a high deeply depth detectors, so maybe that it's not still possible. But still many experiments are waiting to have. So this is our experiment for the AMURET. We are similar to demo. Currently, we are trying to use the same technology we developed for last 10 years. Metallic magnetic calorimeter sensor. This is very small. Fabricated in our lab at Dresden. We are fabricating the detector itself. It's a very small sensor. Speed is fabricated by our collaborator in Germany and the PTV, the Heidelberg University. Make all the sensors made by the experimenters. Not we don't buy the sensors. And this is the crystal is grown by us, and the crystal is grown by our collaborator in Russia. And this is all detectors are basically nothing is made by companies, all made by ourselves. And that's a way we can control the backgrounds level for each materials. So this is the we are running AMURET 1, which is we have about 3 kilograms of molybdenum 100 is included in the about 18 crystals. Now this is the because this is running at the Yeongduk underground lab, which is a little bit higher background environment. So we still have backgrounds not free, and this is the one of the experimental results we presented in the last year. So right now we have new data, and we are almost presenting new data. It's compared the final data coming and will be reported in a couple of months, and we expect this new result from AMURET 1 at the Y2 will be the most leading number will be given because we have more than 400 kilogram data now, and this creepy demo, the previous one reported one was 1.47 kilogram exposure, and they give 1.8. I think we will have from now we will more than 100 will be dominated by the AMURET data from this year. And this is the under construction. We have constructed already most of our parts. This is about 400 crystals we installed, about close to 100 kilogram expected right now. It's a little bit less than 100 kilogram of molybdenum 100 will be installed. This all shielding are already installed. Now we are running the water treatment detector. Run now with check the neon crystal neon data now. And so the recent development, the first set discrimination from the beta, this is the one we expect. CAU, this is all muon signals at the ground level. And this is the alpha backgrounds can be rejected by 2 methods. Recently, we improved this background rejection by first set discrimination, which was not possible before, but now we have some the capability to reject without a light detector measurement. This is one of the most recent new data, and this is the first time we confirm we grown crystal at the Daejeon and inside the lab. And this is the performance of the that crystal grown by in Korean, and that confirmed the alpha background delta, which is generated here. And this is alpha background pretty much can be rejected with a good energy resolution. Still, energy resolution is a little poor than the demo. But most of performance is satisfactory now. So from this satisfactory, the Amore 2, we are this is the current limit in terms of the molybdenum 100 half-life. This is current limit. I'm starting exposure here, and immediately we will be this limit. And we are running 90 crystal from end of this year, and we are running after 1 year running, and we will have upgraded 6 months, and we will upgrade to 400 crystals. We will run after 1.5 years. From end of this year, we will run full scale, and this is the common. Then this is the Amore this benefit from uncertainty for nuclear experiments. This uncertainty from Gen 136 nuclear experiments. So this is the expected from. And another, so there are many physics. In addition to the general we have physics from, for example, solar actions for the lithium 6, and that is also one of the main topics in the Amore experiment. There's another topic shown here from the Smirnov paper in the 2012, and they have some double-dedicated can give molybdenum, especially molybdenum has a shortest lifetime. So that means with the same exposure, molybdenum experiment will have a number of events will be highest. Then you have a 2 is very accurate the spectrum, and the Smirnov's argument is 0 plus to 0 plus state decay and 0 plus to 0 plus state decay. These two are measured. This is almost less than 1% of this one, ground state much better, of course. But intermediate 2 plus state will also possibly to decay. And his argument is if we observe something here, they expected from some said very bosonic neutrinos, some Pauli exclusion principle may be not 100% applied to the, in this case, anyway, these expectations from bosonic neutrinos and Fermi neutrinos are different, especially for this 2 plus state. So there's one of the, in addition to this one, there are many different topics in the neutrino probability. So I have a couple of minutes. So this is one of the experiment we are trying to conceptually pursue with one very large accelerator at the underground coupled with a large detector. That is never configured before, and this is main proposal from the postdocs. Always trying to this kind of configuration may give some new parameter search. For example, this is one of the struggling to know from this target with this accelerator. This is the limitation from the this combined accelerator and the underground detector can cover most of the struggling to know at the low energy, low mass, less than 10 electron volts can be covered. This is one of the interesting. But in addition to that, with the large boson and the very large neutrino detector with the intense neutrino flux, they can always explore some the unexpected phenomena like dark photon, dark matter decay to new bar. And new bar can be easily measured from the large detector. So this is expected some expected signal from this kind of data. This is what we are measuring. So this is one of the example which can be explored with a large intense source underground. So some the pretext may be toward the longest diameter in direct diameter search and experiment. This technology, I think the next speaker will give really interesting possibility for the new techniques. which are very much under development. Cosine has also a lot of features to improve. Usually, diabetic is one of the most one we have to pursue with the multiple elements, unless you clearly resolve the very uncertain nuclear matrix element, which is close to more than 5. So this is we have to run the multiple elements. So more than 100 is one of the must go experiment as far as I can say. So okay, thank you.
Thank you, Yeongduk. If you have quick questions.
Thank you for the nice summary. I believe it's just slide 10, and it shows limits for dark matter and electron scattering boundaries. So here you mentioned the solar reflected dark matter bonds, and then can you explain a little bit more about that? And then is it possible for action-like particles to? I mean, first thing, what is can you explain more about the solar reflection?
That's a good question. So this is we have to ask this theoreticians.
Okay.
So basically, I thought that I didn't really, I missed the reference. There's a reference to the about this possibility. So they have basically also all these things are reflected from the sun. If you have a finite cross-section with that diameter of the electron, that diameter should reflect from sun too. Negatively. That is included. They calculate it.
So to me, is the effect is
humongous. Actually, 0.1 ton data. So that's most sensitive to electrons. So they measure, they calculate that with the xenon detector. Xenon detector limit for a reflected signal.
Right, thanks.
My question may also be for theorists in the audience. I heard about bosonic neutrinos for the first time in your lecture. And it is probably statistics of 2 neutrinos in the neutrinoless double beta decay. No, sorry. No, there is no neutrinos in the final state. I'm not very sure. I first thought that maybe it means that the statistics of neutrinos may be symmetric rather than anti-symmetric. But then I thought that there should be some evidence for anti-symmetric neutrino statistics. And I felt that maybe we are usually told that in supernova explosion happens because of neutrino core in the center. That's possible only with anti-symmetric, right? So I just wonder what this bosonic neutrino is, but maybe I have no idea. If anybody knows, that may be nice. The word is very strange.
But from the experimental point of view, you can measure very accurately to neutrino spectrum. And so
2 neutrino double beta decay. I see.
So this one is
then it's really statistics. I see.
Actually, we already have some number from the sense state decay to this one. So we measured all this from at the Yangnam we measured this excessive decay with the germanium detector. You think gamma rays come down. So 2 gamma ray already measured. We gave a similar limit, a similar lifetime of this one. Lifetime is this is 10 to the 18 years. This is 10 to the 20 years. That's already measured at the Yang. And but we could limit this decay here to here decay. We gave a limit. That limit is similar to what the other experiment gave with the cryogenic detector. This can be also given by germanium detector measurement from these 2 gamma measures. And anyway, I think this is a kind of what we can measure very accurately, the 2 neutron very accurately in the molecular, especially for molecular hability. Not like germanium, they have a less number. 2 neutron number is very small.
Yes, yes.
Three over the same exposure.
I see.
But anyway,
Yes.
so it seems to be interesting to accurate. Also, the shape of this beta decay itself is interesting. The kind of new era we are.
Yes. Yes. Thank you very much.
Our next speaker is Jong Chul from Chungnam National University. This one talks about this experiment.
Thank you. It's like really great better. Okay, so it's new strategy for life into that first based on very recently effective technical based on Christian thing. So yeah, actually we take this experiment as a green because we wanna create the natural method in the sense this is the name of our experiment. So yeah, basically our production is also for like this way. So some portion is based on physics and some portion is based on quantum physics because we should utilize very recently invented technology in quantum physics side. So in that sense, my talk will be something like between particles and quantum physics and something like between theory and experiment. Okay, so yeah, actually the previous speaker already mentioned this kind of wide mass range of dark matter. So among them, this dark blue shaded region is covered by cosine and one and so on because this range is quite well stated and most experienced study due to so-called big reactor. But this region is not because of my talk today. Yeah, my focus will be in this light dark matter region like wind. Okay, so yeah, you can also this light dark matter mass region basically due to their light mass. Similar liquid energy is expected. At the same time, larger flux is expected. So due to the similar liquid energy and larger flux, in most cases, we just focus on lower energy threshold detector used with similar target mass, mostly focusing on electron liquid for more picture and a set of dark matter to target material. So I think you are very familiar with this kind of figure. So this figure shows us current status on dark matter search based on electron liquid. So right hand side is assuming heavy mediator and left hand side assuming heavy mediator and right hand side assuming light data. So as you can see from this figure, there's some limitation on the meso dark matter this kind of in this kind of search. Actually, basically, this kind of limitation is coming from the energy search of each detector. So one good way out for this kind of limitation is if you can make some situation, sometimes if you can have some energy calculator in current universe, then we can easily get this kind of limitation. One good example is the better, but this one is not focused on my talk today. And then in this situation, we can have a kind of question. How can you search much lighter region, something like this KBC region? This KBC, in this KBC mass range, typically expected kinetic energy of dark matter is although milli-eV, so in that sense, expected equal energy even for electron target is at the level of milli-eV. So to find this kind of event, we need new kind of idea, new kind of approach to see this kind of very small energy deposit to the target material. Currently, there are several ideas based on some concept physics side invented idea and sensor or something like that. Yeah, so some ideas based on superconducting material, some one is based on fluid thing. So yeah, and so on. So as you can see from this, the race to prove super light dark matter has already begun. But the current situation is summarized in this figure. So still there is no light such result. Yeah, below MEV region. So in this situation, we want to provide and propose kind of new dark matter such strategy based on recently developed Western junction technology. Okay, so we propose a new concept of dark matter detector, especially focusing on super light dark matter. So this idea can be realized based on kind of state of art of the art technology, the collective based on junction like a single photon detector. So yeah, based on this kind of new technology, we propose new kind of based like immediate vector type search. Name please. Okay, so in this slide, I wanna show what is the key feature of this gravity-based junction device. So the structure is quite simple. So here probably you only see this conical structure here in this region. So this device consists of kind of single sheet or mono layer graphene, located here, and then the two sides of this graphene are joined to superconductor. This dark greenish part, and then these material through the junction, superconductor graphene superconductor is form a kind of superconductor, non-lateral superconductor with junction. And then actually this kind of device is was proposed to cover from GI to microwave photon detection and such. So this kind of idea was several years ago. After that, our collaboration, Prof. Yuri and Dr. Chungnam and their collaborators, they will say experimentally this device work very well as a microwave bolometer. And then this device can have 70 to even below milli energy capacity. After that, so our collaborator also test this device can also nearly work as a single photon detector. So very recently, they confirmed that this device can work very well as a single photon detector for this level of photon, IR photon. So this IR comes to energy equal to about electron volt. And then currently, our members also wanna test this device really work even for single photon detector, energy equals to 1 milli. So this part is under testing, and then this part is already done. Okay, so based on this device, I would like to propose something like new concept of magnetic testing strategy. The detecting principle is quite simple. So we put this kind of graphene superconductor device, graphene-based junction device is located here, and then incoming document can scatter all high-bond free electron inside this graphene layer, and then transform some fraction of this incoming energy to the target electron here. And then this recoil electron heats up and summarize with nearby electron very rapidly via electron-electron interaction. This process happens just within a few picoseconds. After that, this temperature lies in temperature diode electrons in this frequency switch the 0 voltage non-resistive state for Dresden junction to non-0 voltage equal to resistive state. And then by measuring the voltage change from 0 to non-0, we can say, oh, something could in this region, some energy capacity in here or something like that. We can say that.
Check. What happens if dark matter directly touch the superconducting area?
Oh, yeah, actually this guy can touch it and deposit some energy to this material, but heat capacity of this region is much higher than the heat capacity of this mono layer. So in this sense, if this guy deposits some energy in those parts, then the energy stressor should be much larger than this number. So actually we are focusing on relieving energy stressor, so we should find some event energy party in this region. Okay. So actually, inspired by this device, and then based on our idea proposed here, we want to make a much more realistic detector. So such a thing is can be made of based on some multitude of graduation junction array. So to make such a multitude of graduation array, we can scale up simply this kind of structure. So on top of very long graphene strip, we can put lots of superconducting material like this way, and then this is a kind of one-dimensional assembly for a kind of one-dimensional array of superconductor, graphene, superconductor, graphene, superconductor. So each sequence of superconductor, graphene, superconductor represent a single graphene junction device. But if you make this kind of structure, it's quite inefficient because we should put this system in very low temperature, even below 1 Kelvin. So that means we need quite good diode reflector, but due to the size of diode reflector, this kind of long strip design is not efficient. So final our proposal is something like this lower one. So this kind of two-dimensional version of detector unit just simply looks like this jigsaw shape. So here all graphene junctions are connected in series like this way. So that even single switch junction, for example, in this various region, by documented interaction allow some signal resistance between the source and delay. So by measuring some voltage change or resistance change between the source and delay, we can say, oh, some event happened between these 2 points. So we cannot make much more bigger detector, and we can make a much larger scale detector, just setting up this kind of two-dimensional detector like this way. Okay, so next part is something like much more theoretical side. So to calculate experimental sensitivities, we should consider the scattering between documented traveling in three-dimensional space and free electron living in three-dimensional space. However, these electrons are confined in two-dimensional collective layer. So we should reflect this property in our calculation. Okay, so the goal is simple. We want to find some electron label that will scatter for free electrons in two-dimensional collective state. In this calculation, the key point we should focus on is the electron is still confined in two-dimensional collective layer, even after the collision. We are focusing on KB rays like that. So that means the expected energy transfer from document to target electron is at the level of millieV. So with such a low energy, there's no ejection of electron from collective layer. So that means scattered electron will be still confined in two-dimensional frame. So that means there's almost no system momentum change along surface normal direction. In our calculation, we assume this surface normal direction as a z-axis. Okay, the calculation process is summarized here. So basically, if you wanna find some event rate for Univ for 3 times, then such things can be easily obtained by integrating the differential event rate above the energy threshold for each detector. So this one is quite typical equation, and then this typical equation can be extended like this second line, and then by combining this bridge part, we can change like this way. This three-dimensional electron target number state and three-dimensional target mass density. But as I mentioned, our target material is two-dimensional, so we need to slight change this three-dimensional version to two-dimensional version. This one is quite simple trick, summarized in this red box region. And then after getting this slightly modified two-dimensional version of event rate equation, we need to find two-dimensional version of electron target number density. So we want to find electron number density per unit area. This one can be obtained of integrating the spectral expression over two-dimensional momentum space, because here target electron is confined in two-dimensional XY plane. So this guy has only two-dimensional degree of freedom. That's why we need to integrate over this two-dimensional space. And then, so actually we are much more familiar with three-dimensional momentum integration. So we can convert this kind of two-dimensional version into this symmetric version, utilizing a synchronous symmetrical trick. And then the final form is defined this way. Here only difference is this red colored part. So this red colored part is constant with the assumption of no momentum, no significant momentum change along surface normal direction. Okay. But in this equation, you can find some familiar formula here. F and B, and we hide some parallel something like that. This one is gradient surface parallel vector velocity profile. This one is simply obtained by taking a plane cross-section of modified Boltzmann distribution. And then we want to find event rate on two-dimensional material. So that one is by this equation here. So in that sense, also we need to find two-dimensional version of structure function for our event rate calculation. So two-dimensional version of structure function is obtained like this way. So so integrating for the three-dimensional spatial particle is two-dimensional version of delta function with this the three-dimensional momentum of equal electron state at this rate. And by combining this momentum integration with spatial particles with delta function, we can get a second line. So later particle, the second line is just the same as the very well-known three-dimensional version of structure function. So that means the only difference is two-dimensional version of structure function is also this just later part. So in automatically in this structure function, the Pauli effect encoded. Okay, so now we have this master equation for event-related calculation. So I plug in all of the equation and information into this master equation. We can calculate expected event rate for this two-dimensional system. So finally, we want to show some sensitivity limit on this plane. So Dr. mass versus step process between electron and documental. So for that purpose, we need to connect this scattering cross section to this event rate calculation. Here, in this event rate calculation, there appears some amplitude scale. This purple color part. So this part can be connected to scattering protection to this simple formula. So actually we want to show some event some definition prospect. So that's why we assume some simpler case. So also facing a study, many people consider this kind of situation, some settlement between document and target electron through exchange of mediator particle file. So we also assume a similar situation. So in heavy mediator limit, this scattering cross section simplified like this way. Yeah, we can simply make this momentum transfer part. However, in light mediator limit, this meso mediator is much smaller than momentum transfer. So that one is like this way. So each automatic formula can be connected to this event rate calculation. So this simple formula. So in addition to this equation, in our calculation, we consider linear dispersion property of gradient. So this equation, because in our calculation we need to find some Fermi energy of gradient data. Okay, so based on such a calculation, we can obtain some expected sensitivity of our system. So 1,000 level of junction array can cover up to this solid line, depending on realized and accessible our detector. So it can really reach 0.1 milli level of energy threshold, then we can cover this blue color region. And then we can make much larger Gaussian junction array, then we can cover to here this line or dotted line, depending on the number of Gaussian junction array. Then, as you can see from this figure, our Prof detector can improve the minimum detectable mass, documental mass, something like more than 2 to 3 order of magnitude over the ongoing and existing experiment. At the same time, this interestingly, in the case of Latin mediator scenario, our detector is capable of proving the prediction of fringing scenario. The prediction of fringing scenario is constant with this color, this green color line. So our detector can cover this fringing scenario, even with equal to nanogram scale detector. Okay, so actually, I want to say what the property of our detector. So as I mentioned, in our situation, the scattered electron is confined in two-dimensional flattened state, even at the present. So that means there is no significant momentum change or surface normal direction. So the change of momentum, the momentum transfer from documented to target electron happen only for the surface parallel component. So that means the event rate will have documented instant direction. But interestingly, due to the motion of our solar system around the center, we are placing on documented wind from the signal direction. So there's some documented wind direction, but in our system, the angle between incoming document direction and surface normal direction, this angle is quite crucial point in our event rate calculation. So combining these two properties, we will have some additional handle discriminating the signal over some background. So for this one, actually this part is ongoing one. That's why I just put my handwriting. Yeah. So probably we can say pretty understand from the handwriting. But anyway, so in my calculation, we found that there's appear also angular dependence in our calculation here and there, like this way. So reflecting this kind of angular dependence, we can calculate event dependence. The function of theta here, theta means the angle between surface normal direction to the latency and incoming direction. So as a function of this angle, event delay is defined like this way. So that means if the document coming into the latent layer, normal length, normal direction to latent layer, then expected event delay. Normal mean the theta is zero, so the event delay is almost negligible. However, this guy coming into parallel to the latent layer, so the angle is 90 degrees, then the event delay should be maximized. So interesting. So one good advantage of our idea and experiment is for document pending event, issue validation is possible by actually locating our detected system by mount on this kind of tracking system. We can change the angle between layer and copy document reaction, or by checking the time information of each signal, we can in principle calculate the angle between document mean and the surface normal direction. So either way is okay. Okay, so as a short comment for sample side, our proposed detector also can be utilized for the search of other light emission particle, for example, external particle or dark photon. So this kind of process can happen for electron proton frequency. So action is observed by target electron and then converted to photon. So the photon energy is almost equal to the mass of external particle or dark photon. So through this kind of process, our detector can be a good detector search for milli to electron volt mass like cation or dark photon dark matter. Okay. Before closing my talk, I just simply show the current status of our experiment. So thanks to great nice support from Samsung Technology Foundation, this idea is realizing experimentally currently. So this is some part of current status of our experiment. So on top of silicon wafer, we put a large piece of graphene like this way, and then this graphene is encapsulated by hexagonal bond like to protect this graphene material. And then on top of this, we can put some superconductor material, and then utilizing even this graphene, we can make this kind of structure. This kind of structure can be made by like this way. This is real image of our system here. Probably you can better say here, but here is some gray shade region. They don't need gravity, and then yellow shade region is superconducting material. So this is really graphene superconductor graphene array. So we can realize this kind of structure. This kind of structure is quite similar to our surface structure. It's lower left hand side. And then based on our graphene array at the level of 100, so we want to test this one is really has some good property and uniformity or something like that. So we check various uniformity based utilizing this okay prototype sample. So based on our test, this fabricated junction array show very uniform property. The variation is within 10%. Okay, So this sort of my talk brings is a kind of new document detector adopting recently electric reflection from the device. And then scattering between the moving in three-dimensional space and electrons confined in two-dimensional space. Yeah, we should consider this kind of property. Yeah, considering this kind of constraint, we can calculate the expected event rate. And then one interesting property of this system is signal rate will have document instant direction. So due to very nice and wonderful analysis or more analysis of this device, we can have some chance to find some signal induced by K-related the second of target electron. Then, yeah, if our really lies, then we can improve meaning of text over document method up to about some K. Then hot different status like this way, you need for handling for disease and the figures on sensitivity and testing, and then we need some to document the figures of this by statement document. We wanna find additional signal to be used by document or such. Okay.
Yeah, we have some.
Thank you for your very nice, interesting talk. I have a question on the documented directional information. So you have you said there's an angle with respect to the normal direction. So can you say also about directional information on the surface?
So direction information on
I mean the graphene surface.
do you mean the angle? Yeah. So in these two-dimensional space, actually we cannot. Yeah. So we can only distinguish some. We can have some angular dependence to respective to this surface normal direction. Within this surface parallel direction, the electron can
move freely.
So
I see.
there's no free direction.
So then also, I wonder about the time. I mean, the working time of this detector. I mean, I don't know if you can see some annual modulation signal.
Oh, you mean
with this detector?
There's two options. Yeah, if you have really good technical system with enough money, yeah, then you can put our detector on top of it here, and then just changing automatically changing the direction to like this way. Then in that case, can collect so our event as a function of angle, by actually changing the angle between this document mean and something normal direction, it's okay. But if we cannot put, if we cannot mount our detector on top of this kind of technical system, then we just collect timing information and the open which can be converted into angular information. But that one is much more tricky, and we need additional effort and some time. But in principle, the important point is this okay. So our modulation properties some like different from gamma annual modulation. Because, for example, in gamma case, there is an annual modulation and daily modulation, but daily modulation amplitude is much smaller than compared to annual modulation, because the motion of Earth is quite slow. Yeah, if you focus on the spinning thing. But here, our modulation is angular dependent. So even daily, our event rate changes maximize and minimize within 1 day. So in that sense, even collect data within such a 1 month, we can draw this kind of curve in principle.
Kimiko, you have a question?
I'm wondering the sensitivity compared with the electron-positron collider. So maybe for the mediated dark matter case, right, the mediator sensitivity is much better than the electron-positron collider with the monophoton signal. Maybe it seems that the light mediator significance is very, very good. I'm wondering the sensitivity compared with, for example, LEP or future electron-positron collider with the monophoton signal.
I see. So, yeah, so your question is how can you compare our sensitivity compared to collider?
Yes. But cross-section seems very good for light mediator.
So yeah, actually, I don't know. Yeah, the case of collider production, if you focus on very low mass region, yeah, we should consider resolution of the detector system or something like that because their mass is quite tiny compared to the targeted by collider. So yeah, something like if their evaluation something like MEV, not milli, MEV, they said yeah, this kind of very tiny mass particle such is I'm not sure. Yeah.
Oh really? I thought that if momentum is enough large, even tiny, it can be detected.
Based on this. Yeah. But anyway, yeah. So here we just wanna also similar kind of experiment. Yeah, because you know, yeah, based on different type of experiment, yeah, if you wanna convert some expression to the other one, then we should consider some tricky thing between them. So yeah, here, yeah, it's just also very similar one.
I see.
Yeah.
Oh, thank you very much.
Or maybe even such a driver not cover maybe it's kind of is small you can like between documented target but yeah. So one advantage of this kind of thing is for lighter mass we will have much larger plot. That's why we can get this kind of much better sensitivity in this kind of documented detection. That's why we focus on very super light detector with very small size of detector. Actually, we cannot be other experiment in this above maybe region, but we can have much better sensitivity in this region to very nice threshold.
First of all, it was a very, very interesting talk. Thank you very much. Actually, you were confident that this electron, single electron, field's potential. This potential is two-dimensional, and well, I do understand that if we measure the potential, the vertical direction, it's really strong trapping potential. But if I watch this graphene on your slides, I feel that even in two-dimensional, within the plane, there can be some, threefold directions, right? Like 120 degree. And what is the reason why this direction dependence is completely absent in the potential? That's material science, I think.
Yeah, I totally agree with your point. Yeah, actually, our calculation, I also say something like what's idealized version of calculation. In principle, even single layer webpage, there's some text. So there's some possibility of
but have there been? There should be measurement, right? Because if we just put some voltage along different directions and measure the current, and then we can tell if there is any directional, solid state behavior exists or not. And is it measured?
Oh, experimentally?
Mm.
Actually not yet, because this one is very new invented one. So something like
But-
we
but,
wanna calibrate our system as, for example.
But if it is not
measured,
measured, you cannot be so confident that it's two-dimensional. It can be more complicated, right? Then it can be even more interesting.
Oh,
Okay.
Actually, So after calculation, we want to test that sort of thing. Including calculation. One of them is the equity testers. And then what additional thing is, really we can achieve this kind of MSS with very long straight. What should be